All right, this is Chapter 8, Rotational Motion. Today we're going to talk about the very first part of Section 1, which is describing rotational motion. That means we're going to talk about angular, displacement, velocity, and acceleration. Now, when I say angular, I'm talking about circular. So we have two different types. We have straight line movement, and then we have angular movement. So angular, circle, linear, and straight. It's basically the same equations. We just talk about them in radians instead of meters. So you should be able to connect this back to kinematics at the beginning of the year, but now we're talking about it in circles. So you may remember this unit circle. There is no need to memorize them for this class. I'm sure you have to know it for another class.
Yeah.
That's thing I hated. Well, you don't need to memorize it. I'm just showing it to you. You do need to know that there are 360 degrees in a circle, and there are also 2 pi radians in a circle. And that makes 1 full revolution. So that is going to be your big master conversion that you might have to make during this whole time. So we have 1 revolution is equal to 360 degrees is equal to 2 pi radians. So anytime you need to make a conversion from radians or from degrees, that's fine. Now for this chapter, even though we're going to start using stuff in radians, you do not need to change your calculator from degrees to radians. You can leave it in degrees. It only affects your sine, cosine, tangent functions, which we will not be using with radians. So don't bother putting your calculator into radians for this class. Pretty much the only thing that you need from this page I've written on the board right here. Cups. Does anybody want cups? You should come up and get them if you want cups. Otherwise, I'll just pretend like you guys all understand what I'm saying every time. Does anybody want cups? I can throw them at you. But the promise is that I don't hit anybody in the head. Now you wouldn't without no. All right, let's see if we can hit it before. There you go. Nobody else? All right, anybody else? No? Okay. So I see blue cup, blue cup, blue cup. Here we go. So here's our very first one. This is angular displacement. Angular displacement is just like normal displacement, except that it is angular because it's going in a circle. To find this angular displacement, which is theta, that's with the th, theta, it is the total moved in some sort of unit over that same unit, however many 1 revolution is in that unit. So my last class I used pizza because everybody likes pizza, and you guys remember pizza from like 6th grade when we were doing fractions. Imagine you have 10 slices of pizza in your circle, and you move from like 1 piece of pizza down to like you eat 3 pieces of pizza or something like that. So you've moved 3 pieces of pizza. So you've moved a total of 3 pieces of, and your unit would be pizza. Whatever your pizza is. And then how many revolutions are in that pizza? So 10 slices, right? So in 1 revolution you have 10 slices. So it would be 3 over 10 times 2 pi radians. This will give you an answer in radians. Now your book uses this other equation, which is d over r, where this is like your arc length. I don't really like this equation too terribly much because a lot of times you're not given arc length. You'll be given like the radius, and you go 2 pi r and things like that. I like this one better because you can kind of picture it a lot easier. And most of the time you're talking about things in revolutions. So for instance, if you go around the clock or around the circle 4 times, that's 4 revolutions, and there's only 1 revolution in 1 revolution. So it would be 4 over 1 times 2 pi. So that's why I like to use this a little bit better. It makes it easier. But basically what you're doing is saying you're going 2 pi r, and then translating into an angle. If you're going around a circle, 2 pi r. So that's why I like this one a lot better. The units for this theta, this angular displacement, are radians, and counterclockwise is positive and clockwise is negative. So if you look at the clock, you can remember it this way. In a very morbid way, the clock is counting down in the negative direction. You're losing time. It's counting down until your death, right? Morbid. There we go. So you can think of it, the clock's moving negative, and then counterclockwise is positive. I didn't come up with that one. A student did. Not normally that morbid. Okay, I see 2 red ones.
When did you start doing this?
The cut thing? I don't know, like a month into school. I started with my physics 1 because they were really slow, and I don't really want to use it with you guys, but I kind of found that it works. It's just that, like, I think I started with my AP class first because they take forever to go through the homework. But then it kind of spread to the rest of the classes. I didn't really want to do it with you guys because I always give you so much information. Everybody wants to write down every single word. I just have to be kind of pushy. Okay, here we go. We're going to practice angular displacement. And the question says, what is the angular displacement of the hour hand in 3 hours? So you're looking at the hour hand. Let's go over here. The hour hand. What's the total distance it moves, and what's the unit? It goes like 3 hours. 1, 2, 3. So pick a unit. It doesn't matter. Okay, start with the ticks, right? It goes 1, 2, 3. How many ticks does it go on this clock? 3. It moves 3 ticks. 3 portions of 5 minutes or something. 3 of the big ticks. How many ticks, these same ticks, are in 1 revolution? 12, right? 12 ticks. And then multiply by 2 pi. What do you get?
6 pi over 12.
6 pi over 12, which is pi over 2, right? And it's time, so it's moving in the negative direction, and then we're going to put radians here on the end. Now, if we actually do this, I think it's like negative 1.57 radians or something like that. Yeah.
So you don't want just negative pi over 2, you want the exact answer?
I don't care about how you put it. It's the same answer either way. I just don't know how I've written it in there. So, like, if I've done the decimal and you stopped before that, you might just have to do a little calculation to make sure it's right, which is fine. I don't mind. Remember that most of your stuff will be in, like, multiple choice stuff, so you don't really have to worry too much. Okay, so the next question is, what's the angular displacement of the minute hand in 3 hours? The minute hand. Where's the minute hand here? It starts here. What's it do in 3 hours? 1, 2, 3. So it goes around 3 times. It makes 3 revolutions. How many revolutions are in 1 revolution? 1. 1 revolution is in 1 revolution. So what's our answer? 6 pi. Negative 6 pi. Close. Negative 6 pi. All right, and that's about negative 18.8. All right. How do you feel about this? Are you guys ready to try another one, like an actual clicker question on it?
Let's do it.
Clicker question. It's okay, I still have to go over angular velocity and angular acceleration, so don't get too excited. The question says, what is the angular displacement of Earth in 2 days? In 2 days.
I don't know what Earth is. E-A-R-A.
No, we hold it. Let's see. We stop.
Put your questions. I can see when you put it in.
Oh.
Why don't you just put, like how you did the second one? Would you just put revolution or you just put like hours?
Whatever you want to do, as long as the units are the same. Yeah, either way you'll get the same answer.
What do we put it over? I don't know.
Well, it depends on what your unit is.
Days.
Days? So you did what?
2 days.
2 days? And how many revolutions are in a day? In days?
1.
1. Okay. Number 1.
Yeah, it goes around. But it doesn't go around.
I fear for the future of humankind.
Oh, I get it.
Future of Earth kind. That's
How do you know if it's me?
It doesn't matter in this case.
Why?
Because it's just asking about magnitude. If someone's in 3 people, I might leave them in the dust.
No, don't do that. I'm still figuring it out.
Yeah, I think it's the 3 red. You're red.
2 people.
Yeah, you know where I go.
I'm not even on.
I'm just going to put it here.
1 person. Probably Brooke.
It is Brooke, but I'm scared.
Yeah, my cup's getting now.
All right, here we go. It's okay. Even if you get it wrong, it's not the end-all, be-all of everything. All right. Let's look at this in revolutions. How many times does the Earth go around in 2 days?
That one.
2. 2 days, 2 revolutions. Now, how many revolutions are in a day? 1. 1 day, 1 revolution. So it's 2 times 2 pi, giving you 4. Let's do this in hours. How many hours does it take to go around in 2 days? 48. How many hours are in 1 revolution? 24. So 48 divided by 24 gives you 2. 2 times 2 pi is 4 pi. It doesn't matter the unit as long as they're fine. You could also do it in revolutions. What's the revolution? How many revolutions does it make in 2 days? 2, and there's 1 revolution and 1 revolution. Giving you 2 over 1, 2 times 2 pi. It's 4. All right, question 2.
Minute hand in a day?
Calculate the total angular displacement of a clock's minute hand in 1 day. 1 day.
That'd be 24. 24 revolutions, 1 revolution. No, how many times does it go around in an hour? 60. Oh, wait, because the minute hand goes around.
How many times?
No, it goes around. It goes around 1 time. Oh, I did it.
Oh, wait.
No,
That's how many times a
there's 60 minutes in an hour.
That's how many
It goes
revolutions.
around 1 time.
How many revolutions?
It goes 1 tick 1 every minute. That's a minute.
What's 24 over 1? Actually, it's like
I'm so confused.
It goes around.
Okay, 1 day. How many times does the minute hand go around? One day?
In a day, you know?
Okay.
It goes 24 times
24,
in a
right?
day.
So it goes around like 1 hour, right?
So
That's 1 hour. So it'd be 24.
Yeah.
Okay, so 24 times.
Every minute.
24 revolutions.
Over 1 revolution.
Over 1 revolution.
Every
Times 2
hour,
pi.
it
Right.
moves 1
48.
revolution.
On the right.
24 hours.
Just gotta trust yourself, brother. You got this. You just keep second guessing.
She's second guessing me.
Okay, well, don't
second
listen to
guessing
her.
Revolution.
That doesn't make sense.
Don't look at an answer and just feel like this is the answer.
The hour
She's
hand
stubborn.
does 1 revolution.
Isn't there 60 minutes in an hour?
Yeah.
And doesn't the minute hand move every minute?
Yeah, but it doesn't make a revolution.
Oh,
that's right.
Because every hour is like 1.
that would be negative.
Assume that it's talking about areas.
No, 1 revolution.
That's why I always try to think about it in revolutions.
Honestly, this is kind of it's placement.
24?
Oh, it's not.
Negative.
So you're saying D?
Is this what?
I put D in.
Is this all in 8.1?
No, no, we're going to do angular velocity and angular acceleration next. This is the hardest part of the whole chapter. Yeah. In my opinion.
What do you put on the bottom?
What?
What do you put on the bottom?
On the bottom? How many revolutions are in however many units that is? So what did you pick as your unit? Hours?
Yeah.
So how many hours is in one revolution?
So we're finding the radius of the car.
Hours.
What? Because the minute hand goes around. You're thinking about the hour hand. We're talking about the minute hand. 1 hour. 1. Okay, we're missing one person.
What's the number?
No, 24 hours on top. And then one,
Yes, you did.
one revolution on the bottom.
Okay, here we go. In this case, there's a couple of ways you could have done it. How many hours are in one day? 24 hours. How many hours are in one revolution? One. One revolution. Like that, the minute hand goes around 24 times, and there's one revolution in one revolution. So it's going to be 24 times 2 pi. And it's negative because it's long. Okay, let's think about it in minutes. How many minutes are in a day?
60
times 24. Right. 60 times 24. How many minutes are in one revolution? 60. So it'll be 24, because the 60s are going to cross out, 24 times 2 pi. So it doesn't matter your unit, as long as they're the same unit, you'll be fine. There's too much giggling. I don't like fun. All right.
I feel like that's a lie because I really feel like you do that.
All right. This funny little W is called an omega. Omega means angular velocity. It's just like velocity, except for it's angular, because it hates you. All right. So this is, just like velocity is displacement over time, angular velocity is angular displacement over time. And it is in radians a second. Basically, it's how long does it take to move from one spot on the circle to the other spot on the circle. Now, what's nice about this angular stuff, here's a circle. Let's say you move from here to here, so you're going this direction. It doesn't matter if you're here or here or here. You see that as you move further out, your displacement gets larger and larger and larger. Can you see that? The whole thing is always going to be the same angular stuff. So angular displacement, let's say this is 78 degrees. It doesn't matter if you're super close to the center or out, like on the outer edge. You move 78 degrees. So that's why we have this angular stuff. We can translate this into normal linear stuff by using a couple of equations, which I'll show you a little bit later. But that's why we're liking this a lot more, because we don't have to know exactly where we're at on the circle. We're just looking at the turns that it's doing. Once we know the radius, then yes, we can worry about how much it's actually moving. But we're really just interested in what's the change in angle here. So even though our velocity will be changing based on our radius, our angular velocity should be constant because it's turning through that. Whereas if we're looking at normal velocity, we know this is going slower than this on the outside. Because the outside has to move a lot more in the same amount of time to speed up and catch up with the center. All right. Do I see?
Yes, you do.
Yes, I do. There we go. It is so gloomy outside. Some part of me wants it to rain really hard.
I want to be
Reminds me of home.
Is it still hurricane season?
Till June. Yeah.
Wait, I think it ends in November.
Nope.
So we could have
No, you're right. I think it's June 1st to December 1st. I was thinking about starting in June. I was like, no, it doesn't end till June. Yeah, it's supposed to be, I think December 1st is when it cuts off.
So are you saying there's a hurricane?
Huh?
Are you saying there's a hurricane?
No, I'm saying that I really want it to rain. Okay, are we ready? Are we ready? Yay! The next and last equation, well, no, not really last equation. I'd like to pretend like this was the last equation, is angular acceleration. This funny little fish shape is called alpha. Alpha. Alpha is angular velocity over angular time. And this is not angular time, just normal time. There's no angular time here. Radians per second squared. Do you like the fish?
Taylor likes fishing.
Obviously.
See, now that looks like a shark.
It looks like a shark. Really? Sharks do know it looks like that.
It has a fin.
I mean,
All fish have fins.
I don't really know what fish that looks like. Right in top of like a unicorn fish.
We get extra points for making our variables like really
So what?
No.
creative.
Narwhal.
Shit.
No creativity here. It sounds too much like fun.
I mean, we could really hate it instead of doing it.
Brooke, are you finished with your cup? All right. We're going to practice angular velocity. It says Mars rotates every 24.6 hours. It has an average radius of 3.4 times 10 to the 6 meters. What is its angular velocity if there's a rock sitting on the equator of Mars? So, what are we looking for?
Angular velocity.
Angular velocity. Excellent. So we're looking for omega. What's useful here? One of the equations is useful, yes. Which equation would you think would be useful?
The one with omega.
The one with omega. Wonderful.
It's not happening.
Okay, so what do we need to know? The time. Does it give us time?
24.6 hours.
24.6 hours. What's wrong with this time?
In hours.
In hours. How are we going to get it out of hours? Dimensional analysis. There's 3,600 seconds in 1 hour, which gives you, check my math here. I made a mistake earlier, so I don't trust myself anymore. 0.86 times 10 to the 4 seconds. That look right? Okay. What else do we need to know? Look at the equation. Theta. Delta theta in this case, but we'll just call it theta for now. It's fine. How are we going to find that? How about that equation?
Yeah.
How much does it move in, let's say, 24.6 hours? One revolution. It moves one revolution in that amount of time. How many revolutions are in one revolution? 1 times 2 pi. So 2 pi radians. Now what do we do?
Because it moves in 24.6 hours.
Yeah, the top one.
Here's the top one. Thank you. I'm glad someone's paying attention. This is 2 pi radians
You're doing it for Mars.
over 8.86 times 10 to the 4th seconds. That gives us 7.1 times 10 to the negative 5. Radians of seconds. How do you guys feel about that? You notice that it gave us the radius and we didn't use it?
Yeah, so you got the wrong answer.
No.
You just
That's not the wrong answer. Did you get it? Oh. Okay, so now that I did this one for you, sort of, what is the angular velocity of a rock sitting on the equator of Earth?
Okay, I got this.
Earth. You guys making fun of me or him?
You're including
We're making fun of you.
Your noses are not.
Okay, wait. Angular velocity. So it's change in delta. Theta. So what's theta?
So is the radius?
2 pi.
Radius means nothing in this case.
Over there.
Okay, so
What?
2 times.
Where do you
Because it has one
Oh, fourth block line. Third block line.
You use the same one, right?
So 2 pi. It's the same thing.
It can't be the same thing.
I see the equation. Yeah, that makes sense. The change in theta is the 2 pi, right?
The change in theta
It's 2 pi.
is going to be 2 pi, yes, for this one.
Because it's up there.
There's no way it's that.
I want to know how much because you do it's one resolution.
Wait.
There.
You have to multiply, not divide.
No, you don't use one.
No reason to get all huffy and argue about it. Everyone's entitled to their own answer. Just might not be right.
You forgot the pi.
How would you do here?
Hold on, let me get that.
Is the change in time 24.6 hours?
On Earth?
Oh man.
Just delivery fee.
I'm going to do that.
I didn't see that.
I'll provide fees.
Isn't it divided by your?
I was asking.
Look at this. What's the time of one revolution on Earth?
24.6 hours.
So this should be, no, on
24
Earth.
hours.
24 hours.
24.
On Earth.
24 hours.
24 hours. Then a day. So this should be 24, which will give you this. And how many revolutions does the Earth make in one day? One. How many revolutions are in one revolution?
One.
So you can use this.
Okay.
Does that help you, Kayla?
When's next week?
You just got me all sorts of use them.
Huh? Top of the 1 hour. That's 3,600 seconds. Because it's 60 seconds in 1 minute, 60 minutes in 1 day. I just cheat and use this short one.
You just got me confused. All the time.
How many hours are in 1 day on Earth?
24.
24. So that's why we're using 24 instead of 24.6, because the 24.6 is on Mars.
Yeah, we're not Mars.
So why can't we just use 20? 24 hours?
Because it needs to be in radians per second, SI units. So you have to convert to seconds. Just like all of our velocities are in meters per
So we can
second.
use 24 times 360.
3,600. Close.
I'm here. I'm sorry I'm here because next grade I'm working. Yeah. Miss Phillips, I'm being bullied. I'm being bullied.
You're being bullied?
I am.
Nobody talked to Brooke.
Just let it happen.
No. No. Be nice. Be nice.
Nobody shoots a rotation. Isolate. Do it. Don't let my
So we do 2 pi over.
So
So be 2 pi over 840, 64.
I don't know. Maybe. All right, let's check your answers. Check your answers. Your answer should be 7.3-ish over 10 to the negative 5 radians a second. Ignore it says revolutions. You have it?
Actually, we got 72. As in she.
You might have messed up like this part. They're just the 10 thing. You got it.
Or close.
All right. You guys ready for angular acceleration?
No, man.
I don't know.
Wait, were we supposed to put that in?
No. These are just practicing. It's when it's a clicker question, it says question number at the top.
Remember when Colin was scared of Keith?
Let's get the next question.
That was angular velocity.
That was angular velocity. Now we're going to talk about angular acceleration. It says a washing machine rotates 850 revolutions a minute. Now you need to translate revolutions a minute into radians a second. You might want to write that on your paper because your homework is going to do that a lot. It takes 12 seconds to slow down to a stop. The radius of the drum is 0.25 meters. What is the washing machine's initial angular velocity? This is what it's asking for in radians a second. So let me clear off the board here.
Miss Phillips, how come you weren't at homecoming?
What?
How come you weren't at homecoming?
Because I don't like to watch teenagers grow up each other. Yeah, that's what I think. So
That's exactly what happened.
that's why I don't go to homecoming. My first year I went to homecoming and prom, and I think the winter one too, or something. Maybe there wasn't a winter thing. I can't remember. I went, and when I went for prom, they made me work the drink table the entire time because the people that said they were going to show up never showed up. So I don't do that anymore because I just get taken advantage of. Also, I have vertigo, and anything dark and flashy kind of makes me crazy. Makes me fall over, so we don't do it. I can't go to plays, I can't go to movies, and I'm pretty sure homecoming and prom would probably mess me up too.
Yeah,
homecoming was really.
They had a
Strobe
light.
Yeah, that would make me be on the floor vomiting everywhere, so we don't do that. Yay, Virgo. It's great. Okay, so the one up here says, what is the machine's initial angular velocity? You're looking for omega initial. What's omega initial? Kind of tricky. It's got to be one of those numbers up there. Nope, that's radius. It's not 0. 12 seconds. That's the time. That's what we want. 850. No, we want angular velocity, not time. 850 revolutions a minute. That's why you didn't notice it. Because it's a weird unit. So we need to get it into units we like. So we're going to take revolutions, turn it into radians, and minutes, and turn it into seconds. Make sense? Okay. So if this is revolutions a minute, what should we, it doesn't really matter which one we change first, so which one do you want to do first?
Go to seconds.
Seconds. Let's go with seconds. So this is revolutions a minute. So we got to go minutes on top into seconds. How many seconds are in a minute? 60 seconds in 1 minute. Then we got to get rid of this revolution. What are we trying to turn it into? Radians. How many radians are in a revolution? 2 pi radians in 1 revolution. That comes from up here, just in case you were wondering. Okay, let's do some math. Oh, and if we do the math, because I'm magic, 89 radians a second, right? Because you'll have revolutions goes away, minutes goes away, you got radians per second. Magic.
Right.
Yeah, you did last year.
That's right. Okay. So then, what are we looking for? Oh, we already found what we're looking for. So this is the answer to that question. Now I want to know, what is the washing machine's angular acceleration? So now what are we looking for? Angular acceleration, which is a fish, right? Angular acceleration. Okay. So what's the equation for angular acceleration?
The last.
The last one. The change in angular velocity over time. Do we have the change in angular velocity yet? The change in angular velocity yet? All right. Okay. Let's go back. Look at the question. We have 12 seconds. What's this? Time. What's this? 0.25 meters. Radius. What else is in there that's hidden that's not a number but should be? Stop. It says stop. So that's a 0, right? Radians a second. What is that? It is something final. What'd you say, Seth? Omega. Final. Angular velocity final. So basically it starts at 89 radians a second. It takes 12 seconds to slow down to a stop. Good? No? Okay, so now we can put this in here. What number goes first?
89.
It's the change in, so it's going to be 0 minus 89. Remember, this is always final minus initial whenever you have this angle or this little triangle. Over your time, what's time? 12. So we have radians a second over seconds. Is that going to be a good unit for us? Radians per second squared is angular acceleration. So yes, it should be 89 divided by 12, giving us 7.4. Okay. How do you guys feel about that?
Wouldn't that be negative?
Yes, it would be negative. Does the negative make sense here? It starts out in the positive direction, and the angular acceleration is in the negative direction. What happens? It slows down because they're in opposite directions. It does not slow down just because acceleration is negative. It is a combination of the two things. Good?
Yes.
Okay. Let's practice. Oh, here's my answer. Oh, we are almost. No, we're not almost out of time. We have enough for this. This is in your book. You do not need to write it down because it's already in your book.
What page?
I don't know. Somewhere in there.
Looks like a bird just looked at the chapter. Are you Miss Phillips?
199.
And you didn't say this.
Correct, it's 199.
Thank you, Miss Phillips.
You're welcome. The only thing that's really important here is these translations. We're going to talk more about these tomorrow, but I wanted to give them to you. This is actually an X instead of a D. It's easier if you think of it as X. So displacement, velocity, acceleration. Over here you have theta, which is angular displacement, omega, which is angular velocity, and alpha, which is angular acceleration. Notice that you just take your angulars and multiply it by the radius, and that will give you the linear stuff. So that's pretty nice. So that'll help you on some of your homework questions. And I do apologize for how cold it is. They said they're working on air conditioners, so it's going to freeze us out for the next 3 days.
I'm fine with that.
Yeah.
I like it. It's eating on the first word of the month.
Good.
It's fine for that. I like the
All right.
Oh, you're messed up for that.
Here we go. Question 3. I want you to calculate the angular velocity of the cart performing 10 revolutions a minute. The wheels of the cart are doing this, not the cart itself.
Was this like peanut butter?